a little bit just kind of the life cycle of a star. Where do stars come from?
Nebulae,
Nebula. What causes a nebula to collapse?
gravitational force,
Great. So here you have this nebula, this huge cloud of gas and dust out in space. Gravity causes it to collapse. As it collapses, it gets more dense and hotter. At some point, it gets so dense and so hot that fusion occurs, right? And when that happens, dun, 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 you have a star. What's the main fuel of a star? Hydrogen turning into helium. Okay, fusion process, hydrogen turning into helium. This, when a star is doing this, it will be very stable. The sun is in this process right now. It's fusing hydrogen and helium. It's very stable. On the Hertzsprung-Russell diagram, what do we call the stars that are in this part of their life?
main sequence.
Main sequence stars. Great. So these are the main sequence stars. Okay. Eventually, the amount of hydrogen will start to diminish, and there won't be enough to sustain fusion, and the star will start to burn out. When that happens, the core of the star, where the fusion is taking place, actually collapses. It starts to collapse in on itself because of gravity, which causes it to heat up and compress, and it can start fusing helium, the stuff that was the byproduct of the initial fusion process. So the core collapses, helium starts to fuse together, and it starts to release even more energy, which causes the outer layer of the star to expand. When that happens, what's it called? What's it become? It becomes a red giant. Okay. Our sun will do this in more or less in about 5 billion years. Okay. Becomes a red giant, burns for a while, eventually starts to run out of fuel completely. And for just a average to small size star, after it becomes a red giant, it will very gently create a planetary nebula. It'll lose its outer atmosphere and create a planetary nebula. And then what'll be left? A white dwarf. What do you know about white dwarfs? They're really small and they're really hot. They're really small and they're really hot. Is fusion still happening? No. Why are they so hot then? It's just leftover. It's just like a leftover ember. It's like the nugget of hotness that was the star before. Okay? Great. That's the fate of our sun. That's what's going to happen. Okay? And anything smaller than the sun, that's what's going to happen. Pretty exciting stuff. If you are a little bit bigger than the sun, you become a red giant, or maybe even a red supergiant. Okay? Is a possibility if you're supermassive. And as that star, a more massive star, reaches the end of its life, it doesn't give off a nice little gentle planetary nebula. What happens instead? Okay, you get a huge explosion, which is called a supernova. And in that, a huge amount of debris is flown out into space, a nebula is created, and the core, again, collapses in on itself, and what does it become? A neutron star. Great. And a neutron star is incredibly dense. There's no more space in the atoms. The electrons have collapsed into the nucleus, bonded with the protons, become neutrons. It's just neutron, neutron, neutron. There's no more empty space. They're incredibly dense, incredibly small, about the size of a city. They spin really fast. They have these jets of energy spewing out of them because of the magnetic field. And if we are lined up perfectly, so those jets of energy happen to be hitting the Earth, what do we call it? It's then known as a pulsar. A pulsar is a neutron star that is aimed just right so that as it rotates, we get pulses of energy from it. Okay? They are the same thing. If it's even more massive than this kind of a star, after it goes supernova, what will it become? Black hole. It'll collapse into a infinitely dense little point and become a black hole. Let's see. So what is it that prevents a white dwarf from collapsing any further?
The charge,
The electrons. The electron degeneracy pressure. The electrons are repelling each other, preventing collapse. How about a neutron star? The neutron degeneracy pressure. And then if you're even more massive than that, the neutron degeneracy pressure isn't high enough so that gravity can collapse it all the way down. Now, one of the other cool things about this whole process is what gets created from a supernova? The neutron star, but there's also a nebula made. And the whole process starts over again. Okay? So stars do get born, they live, they die, just like almost everything else that we know. kind of a neat thing. And the sun and our star and our solar system, we know has, well, our sun hasn't done this, but basically everything that we're made of is the result of a star that lived before us and went supernova and exploded. So let's review the HR diagram. Hertzsprung-Russell diagram. These guys, Hertzsprung and Russell, they cataloged thousands of stars, and they looked at two qualities that they measured against one another. What did they graph on the x-axis? Temperature. And how does the temperature scale go? Hot to cold. Great. What do they measure on the vertical axis? Luminosity. How much energy the star is giving off every second. Okay, great. They found that 90% of the stars, when they did this, fell into this big swath right here. What's it called? The main sequence. And our sun is right about there, somewhere in there. They noticed 3 other groupings of stars when they did this. One of them was right about down in here somewhere. What's that called? The white dwarfs. And then up here, red giants. And up here, red supergiants. Okay. So it's kind of cool. There's something going on here they discovered. But a couple things that you need to recognize about the Hertzsprung-Russell diagram. We could label these axes 2 different ways. We could say luminosity. We could also call this absolute magnitude. And that would work as well, magnitude. And then on the x-axis, we could say temperature, but we could also say spectral class. Okay? IB expects you to know both of these things. Okay? You could say spectral class. And you should know the spectral classes. And here they are. Are you ready? The spectral classes on the Hertzsprung-Russell diagram, I'll give it a different color here, would be O, B, A, F, G, K, M. O, B, A, F, G, K, M. Those are the spectral classes from hot to cold on a Hertzsprung-Russell diagram. You might be wondering why they chose that order. And I think the reason they chose that order is because the order was created before the Hertzsprung-Russell diagram was created. So they classified stars as class A, class B, class C, or whatever. And then that's my understanding. But how are you going to ever remember OBA, F, G, K, M? Yeah, here's the mnemonic that most people use for this. Oh, be a fine girl, kiss me. There you go. And if you prefer to be kissed by guys, you can say, oh, be a fine guy, kiss me. But either way, or if you want a goat, you can be, oh, be a fine goat, kiss me. Whatever it takes. That's the spectral classes, okay? Lastly, IB would like you to know that these axes, the scales on the HR diagram, are not linear. These are logarithmic scales, okay? So temperature decreases logarithmically, and luminosity increases logarithmically on this diagram. It's not a linear relationship. So, and also you should just kind of recognize that, hey, here's our sun, and then later on our sun's going to become a red giant, and then after it becomes a red giant, it's going to go become a white dwarf. So there's kind of a pattern to how the stars move on this. A star down here, a little M-class star, eventually will do that and do that as well. And if you are a really big, O-class star, you'll become a red supergiant someday, and then you'll go supernova, and you just leave the diagram altogether. You won't be there, okay? Because neutron stars aren't on there. You can't see them, right? Someday. Okay, you guys. So we're moving into the second topic of the astrophysics syllabus, and the first one you already know. E21. State that fusion is the main energy source of stars. Go ahead. Beautiful. You guys got that one nailed. No problem. We can do that, okay? You should understand that in a stable star, there's an equilibrium between radiation and gravity. We've kind of talked about that. Today, we're going to talk more about what luminosity means and how to define that. There's that word define. Please be wary when IB says define that you need to specifically know what luminosity means, what apparent brightness means. We'll talk about the Stefan-Boltzmann law. We'll describe different types of stars. We already kind of have. Discuss characteristics of binary stars, spectroscopic and eclipsing binaries, and identify the general regions of the HR diagram, which we just did. Okay, so there's the sun. What is it? It's a star. But what is it?
It's
It is a main sequence star, but what's it made of?
helium, hydrogen,
Mostly hydrogen and helium. And in what state? Solid, liquid, gas?
plasma,
Trick question. It's a plasma. Okay, so it's a big hot ball of plasma that's fusing. Where's the fusion taking place?
core,
Down in the core. Why in the core?
because it's hotter than pressure out.
You need high temperature and high density. Good, beautiful, excellent. It's a big object. Okay, we had a big old dance. Is it this weekend, the Sadie Hawkins dance? So the son decides to go to the Sadie Hawkins dance, and it's like, I need a necklace. I want an earth necklace. I'm going to make a little earth necklace for this dance. And you know what? I will need 343 Earths to do that. That's how big the sun is, okay? From us, it is huge, but please do remember, in the star's perspective, it's pretty average. That's kind of average size, all right? It's pretty darn massive, all right? It would take 333,000 Earths to have the same amount of mass as the sun. So it's pretty massive. And the volume, we don't have a thing for the volume here, but it's also huge. It's also huge. There's a picture of it. That's an actual picture. You'll notice the dark spots, which aptly are named sunspots. And the sun has spots on it. And those are just cooler regions of the surface that happen because of magnetic storms. And the sun goes through a cycle of sunspots, an 11-year cycle, where it'll have a lot of sunspots and then not very many, and then a lot, not very many, every 11 years. Yeah. Boring. So you should definitely know that the sun is mostly hydrogen, mostly like 73% hydrogen. You don't need to know these numbers, but it's mostly hydrogen with some helium, and then a little bit of everything else. And this is how we know the sun is not a first-generation star. We know it's either second or third or fourth generation star because it has these heavier elements in it that it has not created itself. It hasn't fused those because it's just fusing hydrogen to helium. If you find a first-generation star, one that was like, this is its first go-around, it's just going to have hydrogen and helium in it. It won't have created these other elements.
How do we
So we've discussed this already. We'll kind of review it again, but obviously, you know, the gravity is trying to crush the sun. Gravity is trying to pull it all in. The nuclear fusion is balancing that out and creating radiation pressure outward, and this is all keeps it in balance. But the fusion is taking place down in the core. Here is a very, very, very simplified version of the nuclear fusion process going on in the core of the sun. You don't need to know all the details, but you should recognize that it takes 4 hydrogen nuclei combining together to create a helium nucleus as well as some energy. That's the basic process, okay? It's known as the proton-proton cycle. The proton-proton cycle, which is weird because it takes 4 protons, but they call it the proton-proton cycle, and if we were to do a nuclear equation, here's roughly what it would look like. There's multiple steps in this process, but ultimately you start with 4 hydrogen, you end up with a helium, and 2 positrons, 2 electron neutrinos, and 2 gamma rays of energy. And every time this cycles, you release about 26.7 million electron volts. You don't really need to memorize this number, but that's not a huge amount of energy for one fusion. One fusion reaction, one cycle of the proton-proton cycle is not a huge amount of energy, but obviously it's happening a lot, and so a lot of energy gets released. Okay. To give you an idea, the sun radiates about 3.9 times 10 to the 26th watts, so that's like 650 billion kilograms of mass being turned into energy every second. 6.5 billion kilos every second are being converted to energy. That's a lot. And when you do those calculations, obviously the sun's really big. They can figure this out, that the sun therefore should live to be about 9 billion years old. And our solar system is about 4.5 billion years old, so that's why our sun is middle-aged. It's right in the middle of its lifespan right now. Okay?
Wait, that's 10 to the 12.
Let's talk a little bit about stars and kind of what is it that determines where a star is on the main sequence of the HR diagram? It's temperature and luminosity, but what differentiates, you know, a little red star from a blue star? It's mass. It is mass that determines how hot it'll burn and how bright it'll burn. Okay, so mass determines where it is on the main sequence. Very low mass stars burn very cool and they're very small, but they live a really long time. Little red stars can live like trillions of years. There's little red stars that have been around since the beginning of the universe, except for there weren't stars then. But as soon as stars formed, they were there and they're still here. They haven't died yet. Average sized stars like the sun, yeah, about 10 billion years for their lifespan. So they're burning hotter, they're using more fuel, they're a little bit bigger, they're a little bit brighter, but they live a little bit shorter. And then the rock stars, the really big ones, they're like pumping out energy, they're bright, they're big, they're psyched, but they die young. It's very much like life. It's kind of, you know what I mean? There's a picture of the sun. Do you see the person?
Yes.
See the little person at the bottom? Okay, there you go. Moving on. Luminosity. Luminosity is, any ideas? How what? It has to do with how bright something is, and more specifically what we would say is it's the amount of energy radiated every second, or the power radiated by an object. That's its luminosity, the amount of energy per second given off. So it's measured in watts, it's joules per second. And since we're doing astrophysics, we're going to talk about the luminosity of stars, but you could talk about the luminosity of a flashlight or a candle or whatever. How many joules of energy it gives off every second is the luminosity, okay? In stars, there are two things that determine the luminosity of the star. What would those two things be? Size and temperature. And those are determined by the mass of the star, right? Obviously, the bigger the object, the more luminous it's going to be. For a given temperature, if something is larger, it will give off more energy. That makes sense because there's more surface area. If two objects are the same size, the hotter object will give off more energy, will be more luminous. And you guys might remember this because I think we talked about it before, but the rate at which energy is given off is proportional to the temperature raised to the fourth power. And this is on the absolute scale. So as temperature goes up, the luminosity goes up radically, right? If you double the temperature, if you double the Kelvin temperature of an object, how much more energy, how much more luminous has it become? Yeah. 16 times. It's 2 to the 4th times more luminous, okay? Because the relationship of luminosity is to T to the 4th. The mathematical equation looks like this. It's in your data booklet. It's known as Stefan Boltzmann's law. And it basically says the luminosity of an object is equal to sigma, which is a constant, times A, which is the surface area, times T to the 4th. So it's proportional to temperature to the 4th. And again, please remember that temperature has to be on the Kelvin scale. One of the things that will be really helpful for you guys with IB physics is knowing some of the geometric equations as well. And these are not in your data booklet. So let's do a quick review. How do you find the area of a circle? Pi r squared. How do you find the surface area of a sphere? 4 pi r squared. How do you find the volume of a sphere? 4/3 pi r cubed. Notice in this equation, L equals sigma A T to the 4th. A is the surface area of the object, and if it's a star, we're going to assume that it's spherical, and therefore A is going to be 4 pi r squared, okay? Surface area of the sphere. Okay? So the Stefan Boltzmann's law, this is a repeat. I don't know why I repeat it, but I just did. The amount of energy given off is proportional to T to the 4th, and there you go. Let's repeat again what luminosity. What's luminosity?
It's the amount of energy radiated per second or the power radiated by the star measured in watts.
Excellent. Very well done, Jim. So it's the amount of energy per second given off by an object. What then, if that's luminosity, what do you think, how would you define brightness? How we see it. Excellent. So brightness is kind of how we observe something. Luminosity is actually the energy being given off. What are the two things that will affect the brightness of an object? Distance from us and luminosity. Great. So there's a relationship between distance, brightness, and luminosity. Okay? And that relationship mathematically has to do with this. Notice that here's a source S, and as I move away from a source, if it's giving off energy, let's say light, it has to be spread out over a surface area that's going to increase with the square of the distance. That's that 4 pi r squared thing. So our relationship looks like this. The brightness of an object equals its luminosity divided by the surface area of the sphere that energy has to be spread out onto, 4 pi d squared. Okay? Another way of looking at it is kind of like this. In this case, it's d because it's the distance from the center or the source or the star to wherever you are receiving its energy. Okay? So that could be the radius of the sphere or the distance between the two objects. Okay? So this is kind of a more of a geometrical law than a physics law, but it's something that pops up in physics all the time. Notice that if I have a star giving off light in all directions, that energy that it's giving off is what we call luminosity, right? And at any given second, it gives off a certain amount of energy. And as that energy moves away from the source, it gets spread out over the surface of a sphere, and that sphere gets larger and larger and larger the farther you go. And the surface area of the sphere gets larger with the square of the radius, right? Because the surface area is just 4 pi r squared. So if I take the total energy given off divided by the surface area of the sphere that I'm on, right, on my little planet here, then I can figure out, basically, that's what brightness is. That's how much energy I receive. Watts per square meter. Okay, watts per square meter for the units for brightness. Which leads us to the magnitude scales. The magnitude scales. So there are these ways of ranking stars by giving them numerical values that allow you to determine which one's brighter and which one's dimmer. And we call those scales magnitude scales. And there's a couple different ones. The first one you should be aware of is known as the apparent magnitude scale. And this is a scale given to objects in the sky for how bright they appear to us. It was originally created a long time ago, thousands of years ago, and it was given us numbers from 1 to 6. And the early astronomers that created the scale, they walked outside, and the brightest objects they could see, they said, ooh, that's a magnitude 1 star. And if it was a little bit dimmer, that's a magnitude 2. And a little bit dimmer yet, that's a 3rd magnitude star. So the scale is weird. It's upside down. The higher the magnitude, the dimmer the object. Okay? And originally there was only 6 magnitudes. 6 magnitude objects were the dimmest objects that you could see with the naked eye. Because when this was created, that's all you could do. There were no telescopes. So they just said 1 through 6, and they kind of categorized everything they could see. As time progressed, we had tools that could measure things more carefully, and we were able to measure that a 1st magnitude object was actually 100 times brighter than a 6th magnitude object. So we're now able to create a more mathematical relationship between the magnitudes. And if you take 1 to 6, there's 5 steps. If you take the 5th root of 100, you will get 2.514, which is exactly, or 512, which is exactly how much brighter an object is each step on the magnitude scale. So a 2nd magnitude star is 2.512 times brighter than a 3rd magnitude star. A 1st magnitude star is 2.512 times 2.512 times brighter than a 3rd magnitude star, and so on and so on and so on. Okay? When we had more precise tools, we were able to measure the apparent magnitudes of these objects more precisely, and now the scale goes well beyond 1 and 6. There's even negative magnitudes now. So, for example, the Sun has an apparent magnitude of negative 26.7. Betelgeuse, which is a really bright star in the constellation Orion, has an apparent magnitude of 0.5. Which one's brighter?
Betelgeuse.
Lower magnitude is a brighter object. So the Sun is brighter. Okay? And also, hopefully, just intuitively, you know the Sun's brighter than a star. But, okay? Now let's see if we can figure out how much brighter the Sun is. How much brighter the Sun is. So what's the first step? So they're 27.2 steps apart on the magnitude scale, right? So if you want to figure out how much brighter one is than the other, you have to take that factor, 2.512, and raise it to that power. So in this case, we'd raise it to the 27.2th power. And that will tell us how much brighter the Sun is than Betelgeuse, or how many watts per square meter more we're getting. So give it a try, tell me what you get. So when you do this math, you see that the Sun is 76 billion times brighter than the star Betelgeuse, okay? That's what apparent magnitude is. Now that's one magnitude scale, it's apparent magnitude, and that's helpful for seeing how bright things appear to us. But again, what are the 2 factors that determine how bright things appear to us? Distance and how bright it actually is, right? If something's really bright, it could be, like if I go outside and I see a bright star, it could be that it's just really a luminous star, or it could be an average star that's just really close, and I can't tell the difference unless I have more information, okay? So there's another scale that helps us look at how luminous objects actually are, and that's called the absolute magnitude scale, okay? And the absolute magnitude scale is a numerical scale, just like the apparent magnitude one. Same idea, the higher the number, the dimmer the object. But the only difference is here's what they've done. They said, hey, what if we took all the objects that we can see and we placed them at the same distance? We just have to imagine this. We have to do this mathematically. But if they were all the same distance away and then we gave them a magnitude scale by how bright they would appear from that distance, that's what absolute magnitude scale is. So it takes the distance out of the equation and it gives us a numerical representation of how luminous an object actually is. Okay? The distance that they chose was 10 parsecs. We'll talk about parsecs later when we get into how we measure distances. And it's the same idea, but let's look at this conceptually a little bit. Alpha Centauri, which is the closest star to us, other than the sun, okay, it's about 4.3 light years away. It has an apparent magnitude of 0.1 and an absolute magnitude of 4.5. Betelgeuse, on the other hand, which is 130 parsecs away, it's pretty far away, has an apparent magnitude of 0.5. Which star appears brighter to us, Alpha Centauri or Betelgeuse? So Alpha Centauri appears brighter in the sky, but if we look at the absolute magnitudes, notice that it has an absolute magnitude of 4.5, whereas Betelgeuse has an absolute magnitude of negative 5.6. So it's actually much, much, much more luminous than Alpha Centauri. Okay? It's like 10,000 times more luminous than the sun even. Make sense? The two scales? Got it all figured out? Good? Okay. Again, here's just a brief overview. Magnitude is a measure of a star's brightness. Absolute is the actual amount of light a star gives off, whereas apparent magnitude is how it appears to us from Earth. So distance plays into apparent magnitude. Last two things we need to talk about are variable stars. Variable stars and binaries. There are some stars that when we observe them over time, their brightness varies. They don't stay the same brightness all the time. They get brighter and dimmer, brighter and dimmer. And those are known as variable stars. And there's different kinds of variable stars, but the most probably famous one and the one that you need to know about are called Cepheid variables. And they were first discovered in the constellation Cepheus. And there was a relationship that was found. And what they found is that these things, they go bright and dim on a very regular scale, okay? And that they, the reason they do this is because the stars get bigger and smaller. They expand and contract on a very periodic cycle. And some of them do it fast and some of them do it slow. But it's each given Cepheid variable has a very regular cycle. When it's bigger, it's more luminous. When it's smaller, it's less luminous. The key discovery that made these things so important is that there is a relationship, a linear relationship between the period of luminosity of a Cepheid variable and how luminous it actually is. And this was huge, because as soon as we can find an object that we know how luminous it actually is, and we can measure very easily how bright it appears, we can figure out how far away it is. So this was a very critical type of star in helping us measure distances, okay? Because we can measure its luminosity once you know its period of oscillations of brightness, and when you know the luminosity, you compare it to the brightness and figure out the distance. Yeah? When we find an object that we know its luminosity, there's a name for that type of an object, and it's called a standard candle, okay? And a standard candle is just something in space that you know how luminous it is so you can measure how far away it is. And Cepheid variables are a standard candle that are really useful up to about 60 million parsecs, a good distance away. We've used other things as standard candles. There's certain types of supernovas that are standard candles because when they happen, they always happen to the same luminosity. Certain galaxies have been used as standard candles because they think that, like, if a certain galaxy is this luminous, and therefore we can figure out how far away it is and stuff like that. But Cepheid variables were one of the important ones early on. Binary stars are the last thing we need to talk about today, and here's the deal. We live around a sun that's like its solo sun, and everything's kind of happy. But about half of the stars that we observe are actually more than one star. They are pairs or even more. In the constellation Gemini, you guys know that the two bright stars in Gemini are Castor and Pollux. One of them, and I always forget which one, but I'm going to say Pollux, but it could be Castor, is actually, it looks like one star to us. It's actually 6 stars, all in orbit around each other. It's 3 sets of binaries. So there's these binaries orbiting each other, and then there's 3 sets of binaries that are all gravitationally bound to one another. And yet we observe it as one star because it's so far away. And I don't know which one it is. It's Castor or Pollux. We're looking it up right now. Okay. So what you need to know, what IB expects you to know, is how we know about these binary star systems, okay? And there's three basic classes: visual binary, eclipsing binary, and spectroscopic binaries. They're all binary systems where stars are orbiting one another. In a visual binary, the stars are close enough, or they are far enough apart from one another that we can actually visually observe two stars with a telescope orbiting one another. Okay, that's what a visual binary is. Pretty easy. And you can just sit there, and as soon as we find a binary system, as soon as we measure the period of orbits, we can calculate the masses of the stars and stuff like that. An eclipsing binary is a very unique situation where you have two stars orbiting each other, and you know they could be orbiting like vertically, they could be orbiting at an angle, but in an eclipsing binary, they're orbiting in such a way that they pass in front of one another from our perspective. They're just totally lined up. So does that make sense? That they orbit in one another in such a way that one of them passes in front of the other one on a very regular basis. And when that happens, the brightness of the star will change. When they eclipse one another, the brightness will change. And we can observe that. We can't see the two stars. It looks just like one star to us in a telescope, but we watch it over time, and the brightness fluctuates very regularly. And I want to show you what that looks like. Record. Okay, here we go. This is a good video of an eclipsing binary. So we're going to the Large Magellanic Cloud, which is a neighboring galaxy. And we're going to zoom in. This is one of our neighboring galaxies. Zoom in a little bit. Okay, there's some stars. Pay attention to that star. Notice, look, its brightness varies. So, and it doesn't vary, like it gets really dim, and then back to normal brightness, and then it gets a little dim, and back to normal brightness. It depends on the stars, but days, sometimes weeks, sometimes maybe even years. But notice what's going on here. So when one star gets in front of the other, it gets dimmer. And a key thing to consider is that, and this, I wish they would have made the video slightly differently. Oh, I wish that didn't. Here's a key thing I want you to recognize, and that IB would expect you to understand a little bit as well. This movie, they made it slightly strange, but notice that the big dip happens in this video when the small star goes behind the big star. You with me? But it doesn't really have anything to do with size. It has to do with temperature. When the hot star goes behind is when you get the largest dip, because remember, a hot star is more luminous. So when it eclipses in the back and disappears, you lose more energy than when it blocks the cooler star by going in front of it, okay? So that's why you get these variations in the dipping. And notice that with two dips, it's basically half the period of the orbit. It's only done half the cycle, okay? Isn't that nice? That's a great demo of an eclipsing binary system. So the last type of binary that we need to talk to are called spectroscopic binaries. Now remember, eclipsing binaries, you can't actually see the two stars. In the best telescopes, they still appear as one star. But just because the brightness varies in a very specific way, we know that it's an eclipsing binary system. Spectroscopic binaries are kind of the same way. We can't see two stars. It appears as one star. But when we observe the spectral lines, they move. And they either move in a red shift or a blue shift when the stars are moving towards us or away from us in their orbits. And just by observing the spectral shift of the spectral lines, we can determine that it's a binary system. It's a spectroscopic binary. And I'll show you a very quick video of what that looks like. Okay, so get ready because it goes fast. It goes fast. The Earth is the green dot. The blue and the red stars are the binary star system. And look at the spectral lines. Okay, watch one more time. Replay. Notice that when a star is moving towards us, its spectral lines are blue shifted. When it's moving away from us, its spectral lines are red shifted. And when it's not doing either, when it's moving perpendicular to us, the spectral lines are where they're supposed to be. And that's how we find these kinds of binary star systems. Okay, last one. You get to see it one more time. Does that make sense? Can you see that?